Today we'll be working on the following problem. Let X be a complete metric space and A be a set of continuous real functions on X. Suppose that for all X, the supremum of f of X over A is finite, is bounded, and prove that there exists a non-empty open set G of X such that A is uniformly bounded on G. Pause the video if you want to work on this problem by yourself. Okay, let's see what is the idea to prove this. Okay, from the condition, notice that, okay, for all X, we have for all X in X, this supremum of f of X is finite over all this continuous function on A, right? So this finite, like it is less than sum of less or equal than m of X, which is finite, right? So this bound m is depending on X. So what we are trying to find is we want to find basically find open set, non-empty open set G, which is non-empty, and M, big M, such that this M is for all X, such that f of X less or equal than M for all X in X and F in A. Oh, X is in G for all X in G. So when X on G, and then F for every F continuous function in A. So this is called uniformly bounded, right? So in order to prove this, let's consider this set. So if we define this E sub n to be the set of X in X such that the absolute value, and then we take the supremum over F in A is bounded by n. We have this sequence of En, right? So it is from the condition we know that X is actually the union of E sub n, and from 1 to infinity, right? Because for each n, when you fix X, then X has to be in one of the set because of this condition, right? So next, we want to prove we claim this, that E sub n, this set is closed in X for all n, right? So in order to prove this, the E sub n is closed, let's say if, for example, if we pick any X sub 0 not in n, E sub n, we want to find a neighborhood of X sub 0 such that for any X in that neighborhood, X is also not in E sub n. Then in that way, then we find that E sub n complement is closed. So E sub n is E sub n complement is open, then E sub n is closed, right? So if X sub 0 is not En, by the definition of E sub n, so we know this F X sub 0, and then take supremum over A. This is strictly greater than n, right? So from here, we know there is some F sub 0 in A, continuous function. And then f sub 0, x sub 0, the absolute value is greater than n, right? Because the supremum of them is greater than. So we can find a particular f sub 0 is also greater than n. Now, because since f sub 0 is continuous, because every function in A is continuous function, right? So we know there is some delta greater than 0, such that, because X is a metric space, right? So such that for all, let's say Y in the in the ball center and X0 with a radius delta in this ball. So basically this is for all the y, the distance between y and x sub 0 is less than delta, right? So when y in here, because f sub 0 is continuous, we know that f sub 0 y, the absolute value, will also be greater than n. You can use the basic epsilon delta argument, right? And now, hence, if we take the supremum over f on A, f of y, the absolute value, is also greater or equal than this f sub 0 of y, which is greater than n, right? So what do we have? If x sub 0 is not in E sub n, we can find some delta, some neighborhood of x sub 0, such that for all y in this ball, in this neighborhood of x sub 0, the supremum of the absolute value of f of y over A is also greater than n. That means, in other words, y is also not in E sub n, right? So E sub n complement is open, which means E sub n is closed. So now we have a complete metric space, which is the union of countable union of a closed set. So from Bayes' category theorem, right? There exists some n such that the interior of E sub n is non-empty. By Bayes' category, right? Category. So let our G to be the interior of E sub n. Then for all x in G, the supreme x in G, right? So of course the interior of E sub n is also is a subset of E sub big N, right? Then this in G, then also in E sub n. So, and then by the definition of f sub x, that's all equal to big N from this, right? So we find this G and we find the N. So this N is independent of any X. So that means A is uniformly bounded on G. right? For all the x in G.